Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at logical connectives. We're looking at symbols that connect statements. So in maths, a statement must be true or false. So something like 20 is divisible by 5, that is a statement because you can determine whether or not it is true. Something like 32 is prime. That is a statement. Even though it's false, it's a statement because we can determine definitively whether it's true or false. An opinion like Fridays are awesome, that's not a statement in maths because you can't prove it true or untrue. So to connect these statements, we have these 5 logical connectives, and we'll go through what each of them means. But I want to point out that sometimes we have many of these in a statement that's a combination of other statements, and just like BIDMAS, we have an order in which we use them. So we use this one first, this one second, this one third, and so on. So that'll become a bit clearer in a second. So let's look at these logical connectives. Let's say I pick a random integer between 1 and 100. So let A be the statement the number is divisible by 4. So that's a statement because you can easily determine whether it's true or false. And we're going to let B be the statement that the number is divisible by 8. So let's go through what each of these means. So this one just reads not A. This would mean the number is not divisible by 4. This here reads A or B. This would mean that the number is divisible by 4 or it is divisible by 8. So note that for A or B, we just mean that either of these is true. So for A or B to be true, either A has to be true, B has to be true, or both. On the other hand, this means A and B. This would mean the number is divisible by 4 and 8. So for A and B to be true, A has to be true, and also B has to be true. They both have to be true. So this symbol here implies that. B implies A means that if the number is divisible by 8, which is B, then that means that the number is divisible by 4. B implies A. If B is true, then A is true. This, on the other hand, means that A and B are equivalent statements. What that means is they're both true or they're both false. You can't have a situation where one is true and one is false. So in the context of what we were saying up here, this would be read as the number is divisible by 4 if and only if it is divisible by 8. So for this final statement here, we have a few connectives. It says not B implies A and B. So to understand this statement, we need to note the order of these. So not would appear first, but sometimes, just like when you're performing addition and multiplication, sometimes you need to change the order of them. So that's where we have brackets. So just like for arithmetic, brackets change the order of the logical connectives. We do the brackets first. So if we look inside the brackets, we have implies that, and we also have and. And comes first. So we evaluate this statement first. So this is saying A and B first, then B implies A and B, and then not the whole statement. So in the context of the information up here, this is saying A and B, so the number is divisible by 4 and also divisible by 8. B implies that, so that's saying if the number is divisible by 8, then it is divisible by both 4 and 8. And the not out the front means the whole statement's not true. So it's saying that it is not true that if a number is divisible by 8, then it is divisible by both 4 and 8. So you might have realized that the first 3 statements, their truth or falsity depends on the actual number picked. So let's say I pick the number 44. So if 44 is the number picked, A is saying the number is not divisible by 4. Well, that's false because the number is divisible by 4. A or B, so it's saying 44 is divisible by 4 or 8. Well, that's actually true because 44 is divisible by 4. It doesn't need to be divisible by 8 for this to be true. On the other hand, A and B requires that both of these are true. This is saying 44 is divisible by 4 and it's also divisible by 8. Now that's false because 44 is not divisible by 8. So for these three statements, we can determine their truth or falsity without picking a number. So if a number is divisible by 8, then it will be divisible by 4. That is definitely true. So this one, the equivalence statement, says a number is divisible by 4 if and only if it is divisible by 8. So that statement would be false. Why is that? Because a number being divisible by 4 doesn't need to be divisible by 8. This does not necessarily imply that. So for the last statement, that would also be false. The thing is, if a number is divisible by 8, it will also be divisible by 4. B implies A and B. That's actually true, the statement in brackets this time. If a number is divisible by 8, it will be divisible by 4 and 8. The not out the front is what makes this statement untrue. So this is false because the statement inside the brackets is true, so the not out the front makes it false. All right, let's now look at some truth tables. So here we're asked to show that A implies A or B is a tautology. A tautology is a statement that will always be true regardless of the individual statements A and B. So here's how we set up a truth table. So we put all the components here. So A, B, we've also got A or B. We do that first because of the order of logical connectives, and then we look at A implies A or B. So how we do a truth table, we put truth values true or false. So A can be true or false. B, of course, can be true or false. So the reason we have 4 rows in this truth table is there are 4 possibilities. Both are true, both are false. A but not B is true. B but not A is true. So T obviously means true and F is false. So let's look at whether A or B would be true or false. So A or B only requires that either A is true or B is true. So if A is true and B is true, then A or B is definitely true. Similarly for all these, the only time A or B is false is if A is false and B is also false. So now let's do a truth table for A implies A or B. So this here requires, this statement here, when you have an implication, requires that if this is true, then this one here must also be true. The only time an implication here can be false is if the first thing is true but the second thing is false. So if A is true and this is true, then the first implies the second is true. So if A is true and the second one is true, then our final statement is true. Now notice if the first thing is false, then the implication must be true. As I said, the only way an implication can be false is if the first thing is true but the second is false. So since A is false, the first thing is false in those 2 cases, our final statement must be true. This is a tautology, it's always true, and that makes sense. If the first thing is true, if A is true, then certainly A or B is true because A or B only requires that one of them is true. All right, let's look at one more example of a truth table. So here we're asked to show that these 2 statements are logically equivalent. So we're going to draw up a truth table again. So we have 2 component statements, P and Q. So let's come up with all the possibilities. Either they can both be true, they can both be false, or P is true, Q is false, or the other way around. So this logical equivalent statement means both are true or both are false. That's what it means for something to be logically equivalent. So for P is true if and only if Q is true, it will be true here and here. This bidirectional implication, it can only be false if either P or Q is false. All right, let's look at P implies Q. Remember, as we said before, this statement is true all the time unless the first one is true, the second one is false. So if P is true and Q is false, P implies Q must be false at all other times it's true. So similarly for here, Q implies P will only be false when Q is true, but P, the second one, is false. So it'll be false here, otherwise it will be true. So our final column is this statement here. It's saying this and this. So for this to be true, both our components here, P implies Q and Q implies P, must be true. So it'll be true here because both of these are true. It will be true here because both of those are true. But it will be false here because one of these is false. And if either one is false, if A or B is false, then A and B is false. So here we have finished our truth table. So how can I show that this and this are logically equivalent? It's because they have the same truth values. Notice that this column here and this column here are exactly the same for the different truth values of P and Q. So that means they are logically equivalent. So that means this statement here and this statement here are logically equivalent, and we're going to use this symbol here. So logically equivalent means, as I said, they're both true or they're both false. For example, a number is even, a number is divisible by 2. They are logically equivalent. Either both are true or both are false. In other words, one implies the other. If a number is even, then it must be divisible by 2. If a number is divisible by 2, then it must be even. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.